17.4 How groundwater moves? Sketch and describe a simple groundwater flow system. Discuss how groundwater movement is measured and the different scales of movement. The movement of water in the atmosphere and on the land surface is relatively easy to visualize, but the movement of groundwater is not. Near the beginning of the chapter, we mentioned the common misconception that groundwater occurs in underground rivers that resemble surface streams. Although subsurface streams do exist, they are not common, figure 17.10. Rather, as you learned in the preceding sections, groundwater exists in the pore spaces and fractures in rock and sediment. Thus, contrary to any impressions of rapid flow that an underground river might evoke, the movement of most groundwater is exceedingly slow, from pore to pore. Figure 17.10 Underground rivers. A common misconception. Although subsurface channels of flowing water occasionally occur, such as this one in France, they are rare. Photo by Michael Collier. A simple groundwater flow system. Figure 17.11 depicts a simple example of a groundwater flow system, a three-dimensional body of earth material saturated with moving groundwater. It shows groundwater moving along flow paths from recharge areas, where groundwater is being replenished, to a discharge area along a stream where groundwater is flowing back to the surface. Discharge also occurs at springs, lakes, or wetlands, and in coastal areas, as groundwater seeps into bays or the ocean. Transpiration by plants whose roots extend to near the water table is another form of groundwater discharge. Wells, where groundwater is being pumped to the surface, are artificial discharge areas. Figure 17.11 Groundwater movement. Arrows show paths of groundwater movement through uniformly permeable material. The force that moves groundwater is gravity. In response to gravity, water moves from areas where the water table is high to zones where the water table is lower. Although some water takes the most direct path down the slope of the water table, much of the water follows long, curving paths. Figure 17.11 shows water percolating into a stream from all possible directions. Some paths clearly turn upward, apparently against the force of gravity, and enter through the bottom of the channel. This is easily explained. The deeper you go into the zone of saturation, the greater the water pressure. Thus, the looping curves followed by water in the saturated zone may be thought of as a compromise between the downward pull of gravity and the tendency of water to move toward areas of reduced pressure. As a result, water at any given height is under greater pressure beneath a hill than beneath a stream channel, and the water tends to migrate toward points of lower pressure. Measuring groundwater movement. The foundations of our modern understanding of groundwater movement began in the mid-19th century with the work of the French scientist-engineer Henri Darcy. One of the experiments Darcy carried out showed that the velocity of groundwater flow is proportional to the slope of the water table. The steeper the slope, the faster the water moves, because the steeper the slope, the greater the pressure difference between 2 points. The water table slope is known as the hydraulic gradient and can be expressed as follows. Hydraulic gradient equals H1 H2D. Where H1 is the elevation of one point on the water table, H2 is the elevation of a second point, and D is the horizontal distance between the 2 points, figure 17.12. Figure 17.12 Hydraulic gradient. The hydraulic gradient is determined by measuring the difference in elevation between 2 points on the water table, H1, H2, divided by the distance between them. D wells are used to determine the height of the water table. Darcy also experimented with different materials, such as coarse sand and fine sand, by measuring the rate of flow through sediment-filled tubes that were tilted at varying angles. He found that flow velocity varied with the permeability of the sediment. Groundwater flows more rapidly through sediments having greater permeability than through materials having lower permeability. This factor is known as hydraulic conductivity and is a coefficient that takes into account the permeability of the aquifer and the viscosity of the fluid. To determine discharge, Q, that is, the actual volume of water that flows through an aquifer in a specified time, the following equation is used. Q equals K, H1 H2, D. Where H1 H2 D is the hydraulic gradient, K is the coefficient that represents hydraulic conductivity, and A is the cross-sectional area of the aquifer. This expression has come to be called Darcy's law, in honor of the pioneering French scientist-engineer. Using this equation, if you know an aquifer's hydraulic gradient, conductivity, and cross-sectional area, you can calculate its discharge. Different scales of movement. The geographic extent of groundwater flow systems varies from a few square kilometers or less to tens of thousands of square kilometers. The length of flow paths ranges from a few meters to tens and sometimes hundreds of kilometers. Figure 17.13 is a cross-section of a hypothetical region in which a deep groundwater flow system is overlain by and connected to several, more shallow local flow systems. The subsurface geology exhibits a complicated arrangement of high hydraulic conductivity aquifer units and low hydraulic conductivity aquitard units. Smart Figure 17.13 Hypothetical Groundwater Flow System. The diagram includes subsystems at 3 different scales. Variations in surface topography and subsurface geology can produce a complex situation. The horizontal scale of the figure could range from tens to hundreds of kilometers. Tutorial. Groundwater flow. Starting near the top of figure 17.13, the blue arrows represent water movement in several local groundwater systems that occur in the upper water table aquifer. The groundwater systems are separated by groundwater divides at the center of the hills, and they discharge into the nearest surface water body. Beneath these most shallow systems, red arrows show water movement in a somewhat deeper system in which groundwater does not discharge into the nearest surface water body but into a more distant one. Finally, the black arrows show groundwater movement in a deep regional system that lies beneath the more shallow ones and is connected to them. The horizontal scale of the figure could range from tens to hundreds of kilometers.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to... So groundwater, you might think of it as not really a flowing entity because it doesn't flow nearly as fast as streams do on the surface. However, there is flow that happens below the ground. If you dig a hole deep enough, that hole will eventually fill with water, and that hole is filling with water because the water is flowing from the surrounding pore spaces into the hole. This is an image showing the overall pattern of groundwater flow. Notice that it's flowing from higher areas, such as underneath hills, towards lower areas, such as by streams. Imagine sitting down on a waterbed and then maybe taking a stiletto or a jackknife and punching a hole in the waterbed. As you are sort of sitting on it, applying pressure, that pressure basically causes the water to flow out the hole that you've created. And so it's sort of the same thing underground. Basically, the hills are areas of high pressure and the stream valleys are areas of relatively low pressure. So the water flows from high pressure towards low. One early realization about the rate of flow is that it has to do with slope. So Henry Darcy established this. Got 2 wells. Those wells start at the surface and they go down and pierce the water table and end up in the saturated zone. You can figure out the height of the water table in the subsurface. Call it H1 and H2, so that's the elevation of the water table. And you can subtract the difference between H1 and H2. So that basically gives you the height of a right triangle. The triangle also has a width, and we can represent that with the letter D. And so using the height and the width of that triangle, we can calculate the slope. This is called the hydraulic gradient. And that's the slope of this surface right here. And obviously the steeper that line is, the faster the groundwater flow is going to be. Another variable that we have to consider is the presence of impermeable rock units in the subsurface. These are referred to as aquitards because they retard the flow of water. So a rock unit that is good at holding and releasing water is called an aquifer. So you've got a large aquifer here shown by the area below the main water table, and then there's also a perched aquifer up here on top of this aquitard. Where the aquitard intersects the surface, you can see there's a series of springs that allow water to leave the perched aquifer and trickle out onto the surface. So if you combine these sorts of realizations, you get a sense that groundwater flows at different levels and at different rates. In the shallower part of the groundwater, you have relatively rapid turnover of the water. So water enters and it leaves. It enters through infiltration and it can leave through water bodies on the surface, for instance. There's also a deeper level of groundwater flow where water leaves areas of relatively unimportant ephemeral streams and makes its way towards major rivers. So like the red arrows here are all going towards that major river that you see over on the left. And then there's really deep regional flow as well, where the groundwater is moving over larger distances and over much larger timescales. All right, let's test yourself here. Here's a situation where you've got a cross-sectional view into some groundwater. What would you say would be reasonable groundwater flow paths for this picture? Well, this little perched aquifer, for instance, could have water flowing out to produce these little springs you see here on the surface. Other water could basically flow off of that little aquitard into the main aquifer here, and maybe you end up having some local flow into these little streams or these lakes. Plus, there would be a larger regional flow that would work towards these major rivers, like the one you see over here. And then there could be regional flow that goes into the deep subsurface and moves over much greater distances and much longer timescales. Very nicely done. Thanks very much for your attention. This has been another Smart Figure.